Before we get started, I do want to thank Dr. Benoit for inviting me here to give this talk and for the sponsorship of both the School of Information and Library Science, School of Library and Information here at LSU, and also the Department of Geology and Geophysics. And most of all, EarthCube, which I'll define what that is later in my talk, but EarthCube is a NSF-sponsored program that is supporting cyber infrastructure for the earth sciences, and they have an early career and distinguished lecture series where they're funding people to talk about their research and as well as how it overlaps with EarthCube in order to raise awareness and increase knowledge and abilities within that area. So thank you to everyone, and thank you all for attending. I'm so excited about this group, and I can't wait to hear where you're all from. And I do get a little interactive, so be prepared. Okay, so today I'm going to talk about what is data. There was some pushback that this should have been what are data, but again, that just leads to this question. There's a lot of talk about the concept of data everywhere nowadays, and we're not really sure how to define it, how to manage it, how to use it, where it fits into our lives. So my viewpoint on it is that physical objects should also be considered as data, and I'm trying to push at the boundaries of that as we're trying to define data. Let's include physical specimens, scientific objects, and other physical materials, and not just digital or published or printed materials. And so I'm going to talk about that concept a bit, and actually, as an outline, I'm going to introduce myself and a little bit of my background, which helps sort of ground the conversation, and then I'll talk about this concept of physical samples as information sources, move into some current projects in the earth sciences, some examples from EarthCube, talk about the role that information science and archives can play into this questioned area in the future, and then just briefly touch on a little bit of my research interests. Okay. So my background is, I have a background in geology, and this is actually me working on a drill rig when I worked for the Florida Geological Survey. I worked as a geologist for 7 years, starting off doing research descriptions of cores and cuttings as a research assistant, and then eventually moving into a field position, working as a driller's assistant, and also managing the information resources at the state survey. This includes physical objects like these, cores and cuttings, which are, I realize I probably should have, a visual would have helped here, but if you imagine sticking a straw into the ground and pulling that straw out, and then you have material within that straw, that is a simplified version of maybe coring and collecting samples that represent the intervals of Earth and what's going on underneath the surface. And the Geological Survey in Florida has a mandate to maintain these collections both for their own research purposes and for outward, either for commercial, industry, academic purposes. And so my job was to go out and collect some of those samples working on the drill rig, but also to then manage them once they were given back to the survey, if they were donated from oil and gas exploration, injection wells, other DOT, other government agencies throughout the state that were collecting samples, and then were told to donate them into our repository for long-term holding. And originally when I was hired, the job description was rebox core. Take them from these wooden boxes that has the metadata written on the box and transform them into these archival collections so that scientists can access in the future. But then there's a transition where it became not just that, but helping to link these resources to the outcomes and the data that resulted. So you might have an actual description of the core that we were just looking at, and then it might be used to map the aquifer system within the state. And so each one of those points or lines as a point is a well drilled down, and we can see the different layers of the aquifer in Florida in this example. But I was no longer doing the research, but facilitating that role and really helping people find these materials that can ultimately come up with these end products. And so during that transition, there was a lot of records management that began to happen, and cleaning up of data and making sure that people could, I used to call it being a reference librarian. People would call and say, do you have samples within this area of research? And I'd have to search through the collection to see if we did, and ask them, well, is there a depth issue? Is there different types of, do you mind if they're cuttings versus cores? Lots of questions and back and forth before handing over a set of data. And it was really problematic. That became most of my time, managing this information access and not actually going out into the field. Like, I didn't really have time to do that. And then I did an internship at the Natural History Museum in London as part of my master's degree, where I thought, okay, I'm going to go to the big show, like Natural History Museum of London, like where geology was born, like this is it. And they also had similar problems of managing their information. And they thought that these things that I was bringing in from library science were really amazing. And it was like, really? So, like, I don't mean that to say that geological institutions, science institutions aren't doing amazing work, but there's a burden on having to also do this other side of the task of providing access to this information and managing the collections. And there's just some skills involved with that are often associated to, oh, you're a geologist, but on the side, manage this collection. And so it's not getting the same attention and funding addressed to it. But I realized when I was at the Natural History Museum that it wasn't just a problem at my institution, that other institutions were having similar issues. And so as I was bringing in these concepts from library science about arrangement and provenance and record keeping and different things, there became like, wow, you are amazing. And it's like, no, I'm not amazing. I'm just a librarian. And there's a whole school of people with these same skills and training. They tend to come from the humanities and need to be trained in the sciences, but they can help you deal with your information. It might be in the form of an object or a rock or data sets as opposed to books and published information. But there's still a lot of strong concepts and roots there that can transform. So again, that's a bit of my background and what brought me to this research topic. Again, working with these samples and knowing that people needed them, but having problems providing access, and for a wide variety of reasons. So now we're going to sort of transition into this concept of these physical samples as information sources. So as a bit of a thought experiment, how would you describe a chair? And as Ed has told me, the video isn't going to record the interactions from the audience, so I'll just do this a little bit more theoretical than a practical exercise. But if you were to ask someone, go get me the chair from the other room, or a chair, you might need to provide a little bit more information. Is it a folding chair? Is it a specific color? Does it have wheels? What other things do you need to communicate to someone so that they know which chair you want and that it's a chair versus a stool, and the extent of their knowledge related to it. But there's a lot of details and information that we take for granted, especially when it's as simple as just an object, like go get a chair. That's easy. So they can bring it back if it's wrong. They can do something else. But there's a bunch of different reasons for why we describe things. And I use this when I teach about organization of information. So some of these aren't necessarily relevant, but there are, again, a wide variety of reasons why I might describe something. But we often describe them, again, so we can refer to them or interact with them in some way. But in some cases, we describe them so we can capture that scientific knowledge about them and create a scientific record. And the record in the archival definition can be in any form or format, and it's something that we keep as evidence. And that's what really brings me back again to this physical object as a record. In the 50s, Susan Bozette suggested that keeping antelopes in a museum, stuffed antelopes, as well as keeping a live antelope in a zoo, was documenting the concept of an antelope, and that each one of those had a different concept it was representing. The live animal that can eat, that can move, and show motion, that captures one set of concepts and ideas of what an antelope is, versus when you stuff it and preserve it in a museum and it's static, you can still maybe find out things about the texture, but you can't take blood samples. There's a level to which it can only record a certain amount of information. And she posited that when it's collected as an object of study, it becomes a record. And records can be structured or unstructured. So again, to pull in this concept of earth sciences, going out and collecting information in the field, writing in your field notebook. There might be unstructured notes where you're just writing out your thoughts and ideas, versus when we actually have formal records where you can think of if you've ever had to fill out a travel request or something, and there's specific fields and boxes that tell you what type of information it wants, and there might be a controlled vocabulary around that. And records come in many different forms. We've got the scientific findings, things coming out of an instrument. If we think about log data or anything coming out of like seismic data, things coming out of machines. You've got, again, these living animals in zoos documenting what it is to be an antelope. You've got the stuffed version or other specimens in a museum that represent the static version of it. You've got press releases, scholarly articles, and other things that are more formalized that we think of as records of scientific knowledge. But really, when we do this scientific record, we're documenting the knowledge. And it comes in many different ways. And again, this is related around earth science, but I've got this concept of explicit, implicit, and tacit knowledge, where explicit, you can see it, you can touch it, it's tangible, it's articulated very specifically. Implicit is, it's not yet made explicit yet, but it might be some uncertainty levels of, well, I wrote down that it was this type of rock when I was out in the field, but I'm not certain entirely until I test it because it could also be something else, but I don't necessarily record that. I just know that based on what I was doing. And this tacit information, that might be the experiences that you have by being an expert in your field and your domain that you've learned over time and experience that don't get recorded in the record or in your final document, but it's there because you've brought it there to the table. And I'm suggesting that rock samples fall into this explicit area because they are tangible physical things that represent the knowledge, and you can still go back to them and pull the knowledge out using different instruments, the individual's eyes, different methods. But it does record an instance. It was specifically picked out of the field within an intentional decision making going on that this is representing some instance, an outcrop. It might be representing a geological unit. It could be a fossil specimen representing what was found in an area at a time, different things, but there was some intentionality, and it represents the knowledge just by being there. But when we go back to thinking about how do we describe these things, what if the chair we were describing was a scientific object? We wouldn't want to just use any language in how we talk about how to find it, how to recover it, how to deal with it and use it in research. And so you might want to have controlled vocabularies, shared understandings of what things mean, what's important, persistent identifiers, other important characteristics that we would describe these things or attribute to these things in order to recover them in the future. And so we don't have that same conversation problem of, well, which chair did you mean? So when you're doing reproducibility in science, it's like, well, which fish fossil did you find this unique, interesting thing in? So you want to be able to distinctly identify what you're talking about. So here are some more examples of physical objects in earth science. We've got a core, which again is that straw metaphor of just a solid sample of continuous materials from the surface below. Cuttings, which when you drill in, you can also just take at different intervals a sample that represents what's there in that time period. And then also here is an example of core chips would have been chipped off of a core but put next to geophysical logs, which were run down the well that are producing other information and sort of showing the connection between the two. That there's like this representation of a zigzag line here that means something that's also being represented by what's in the rock. Okay. So that leads us to this idea that these samples have surrogates that might be either secondary or derived media. We've got this description, which is a physical, someone looking at the rock sample and making a description, discussing what they're seeing in code, and also as a finalized report. You also have other associated data, like again, those geophysical logs that might have been run down the well that represent the rock that we're seeing and what was going on there. And then you have a final output here where you might have different layered maps that are representing taking from these individual data points and making a final larger outcome. But we need to be able to connect all of these things back, and we often do that using surrogates. So in order to be able to search for and find this core again, we've got information written on the box, but you're not going to wander around the shelves and just look at everything. You want to have a step above that, digital records, different ways to access. But there's a lot of issues when we fail to document them properly that can be as bad as the loss of the scientific value of these collections. It doesn't have to be as drastic as losing all of this metadata that's on the box, in the box, associated with it, but that's an extreme example of when the collections are not valued as scientific research and they're just considered objects. The care isn't there, the funding isn't there. And when you lose those connections to that information of where it came from, what purpose it was collected for, what tests have been run, all this other rich secondary information, then they just become rocks and they lose their scientific value. There can be some value in knowing that you have a rock from that represents a unit, but that's not the same thing as knowing it came from this spot at this time and who collected it and being able to associate that back to other reports and information. But then once we have all of this stuff, we want to think about arranging them into collections. And so organizing them and being able to say something about them and retrieve them. And we often do that by bringing like things together around specific attributes. And this idea, again, of intentional arrangement, that someone purposely said, I want to collect this thing for this reason, and it represents this information. It can be a human or a machine, but it has to have agency. So just rocks being out in the field, in the wild, layered, like where you can see distinct units, there might be some differences going on, but they weren't intentionally organized that way. It's not the same thing as if you were to then describe those units and start adding detail to it and have a sample representing something, and eventually maybe even putting stuff on display with labels, like where there's some intentionality involved with the collection. And so that brings us to this concept that there's a lot of archival needs and things from information science that we can bring into this managing of physical scientific data. And coming from the archives perspective, there's really this idea that you want to do record keeping in a variety of ways because there's a variety of uses. And you don't know who your customer is or your client and why they might be interacting with the collection and what they want to get out of it. So there's a built-in concept of I want to make sure this is available to the most amount of people. And that's often something I see within scientific collections is, well, we collected it for this purpose, so the metadata is directed in this direction, but there's not as much thought of people who might be interdisciplinary or coming from a different domain or background who might want to still use those same samples that were already collected and reuse them in a different purpose. And so there's a lot of concepts from records, archives and records management that we can bring into this management of physical samples. That's the focus of you've got records, you've got provenance, original order, we're looking at long-term, the contextual information. There's a lot of different layers to it that you can see where we can apply this to scientific data and not just to humanities and historical data, which was the traditional viewpoint of an archive, is that, oh, here we're holding onto Lincoln's hat, which we know has very national and emotional importance, but what about other things like this scientific data? And then there are a few key principles within information science and archives like persistence, effectivity, authority, and the principle of provenance. So we want to know that what we're looking at is what we say it is. We want to see the order of where it's been through time and what changes might have been done to it. We want to know where to find it in the future. So if it's published in a journal and I disagree with the results and I want to look at it, can I find it to look at it? And sort of transitioning again a bit, I really do think the history of the field of geology really shaped how they currently organize their information and how that's treated within the field. And so there is a need for a cultural shift with these concepts, but it helps to sort of back up a bit and talk about how that was impacted by the way the field developed itself. So you have this concept of curiosity cabinets, the lone scholar going out and collecting things and putting them on display and having societies that came and look at these things in they're fanciful and different and not necessarily in a scholarly way. And with skipping over a lot of details with this slide, you have this transition from hobby to scholarship, where there's this idea now that it's not just an aristocratic role, but something that it's a profession, it's a field. I was talking to Ed earlier about this concept of William Smith, and he dug canals, he discovered this idea of stratigraphy, but he wasn't accepted in society, but that changed because of a lot of work that he was doing. But it was, again, a very personal, individual research focus of like the individual was doing things and was their work for themselves or to share with others, but it wasn't on a larger scale where we might see teams of scientists working together to achieve something. And that shifts over time from the individual to sort of from individuals managing the collections to curators managing collections, where you've got samples going from the individual researcher and being deposited into a repository where now they're being managed as a collection. And in the past, when it was your own individual collection, you had your own methods for organizing them. But going back to that example of William Smith, when he donated his materials to I can't remember if it was the British Museum or the Natural History Museum, they actually paid him later to come back and create metadata for the collection because they realized it did not have the same value without him and his expertise. And there's actually a really great quote from an 1870s scientific journal where they're saying, like, without the metadata, but they're not saying metadata, but without this information, these things are useless. And so they were advocating for spending this money to hire him to come back and do this extra work. But when nowadays we deposit things into a repository, there's not necessarily consistent metadata in how those are recorded or captured before they're deposited. There's not necessarily the adequate staff to maintain and process these samples in this warehouse, in the repository, to create access, and that can be a bit overwhelming. And so, but it's really, again, I feel like tied to that culture of it was the individual, the lone scholar who was doing this work and not thinking about that next step of what happens when it becomes part of a larger collection. And we'll talk about some of the changes in the future with earth science, but we can see where now, like just as a hint, all these White House policies, this change in open data, that you're going to have to fundamentally change how you think about managing and accessing data. So these ideas of, again, scientific data collections is that they may be raw or processed, but it's a way of connecting both the collections of the physical samples or the objects that are being represented, as well as other supplemental things. Again, those surrogates that might represent the collections, but also final publications and outcomes and things that result from the collections. And collections play a number of different roles, and these are really critical within science. You want to have vouchers of, or results of earlier findings. You can think of type specimens, where this is the definitive way we describe this unit or this organism, and we need to go back to it to see if we've discovered something new or if it's a variation on it. There's other types of research that might be done. It might be a rare object. But I think importantly, we come to the idea of reproducibility in science, is that we do want to keep these things so that we can go back and question what was done, find new methods, advanced techniques, verify results, and connect things together. And that's what these objects in these organizations represent. And they come from a lot of different structures, but you can think about the idea that you have the individual sample, and maybe a scientist has gone out into the field and collected their bit of samples, and that's where I've got this is intentional, like the bit of the collection that might not end up into the repository, but it starts off at an individual level. And then you might have a broader area of this is all the things collected for this research direction, and then eventually leading up to like the generalized idea of a collection. But within these collections, there's a need for cross-training. So I'm trying to think whether, because I've got this nice quote, but at the same time it reminds me of just the idea that the Smithsonian was doing a study of digitizing field notebooks with the USGS, and they were digitizing them with the idea of these are archival materials. We're going to put them in the archival order. We're thinking about the life of the scientist and how he worked at this institution in this area these years, and then he transferred to this other institution and worked here for these years, and we're going to put them in order of his life and what he was doing. But those documents are also that rich information about the sample, of where it came from, what was going on at the time, why it was being collected, and if there's missing information in the other records, you might want to go back to that field notebook. And in the case of this Smithsonian project, you would have to know how to look as a historian and not as a scientist. You can't look through it and say, well, where is all this particular unit or this particular rock type, or it's not organized in the same thought process. So there is a bit of need for cross-training and not just managing a collection as a scientist, but also a historian, but also as a view of the users being a scientist. So it's sort of like this mixed concept, like identity crisis. And so moving into thinking about, again, this history and this timeline, in 2002, the National Research Council came out with a report saying that geologic collections were in peril. They were at risk of being lost, and the main two reasons they said were because of improper curation and metadata management. Not to say that they were being mishandled, but just there wasn't that direction and funding, again, focused on those areas, and they advocated for funding to preserve these collections. And around those same times, we can see some examples that were coming out to advocate towards this. This is an article by Lee Allison. Sorry, he passed away recently, so it's kind of sad. But it talks about the value of these collections and how they might be reused for a different purpose than their original collection. In this case, atomic cores collected in the 60s that were then used when there was a gas leak happening in the town and they didn't know where it was coming from. So instead of spending the time and the money to re-core and find this leak, they were able to go look at their collections, determine where the leak might be occurring, and pinpointing it and save lives. But in the same time period, we have the Georgia Geological Survey being closed. Funding was not there. Georgia State needed to make some sort of budget cuts, and they decided the geological survey wasn't of value. But they did value the sample collection in an interesting way, but they didn't provide funding to maintain it. It's still there, you can still go get samples, but it's not an active collection, it's static. So there's this problem area where we've got this decline, this risk of loss of these samples, and part of this needs to be a change in culture. So who are we training? How are we valuing these collections? What is the role of them within our organization? And also, where is the intention on these things? So that we can say that they are critical to our field, they are data, they need to be funded, they need to be preserved, we need access to them. And so along those lines, there's been a number of changes in policy for earth science data, so they're working on this issue. And we can see in Science, the journal, not just Science, they've come up with 8 standards for transparency and openness, and they specifically mention data and codes and samples being accessible. Nature has come up with a similar set of guidelines, and for both of the journals, they won't take effect until next year, but they're advocating both for authors and reviewers to make sure that a standard is met in how access to data is available. And for Nature, they actually have different tiers, understanding that each field has their own different needs, and that access to data, and maybe in some social sciences, might be hard because of privacy concerns, but also different levels of effort needed to create access to collections. So they've come up with different tiered ranges, and they've suggested that they're policed by the domain themselves, that the community will say what they need and what is acceptable as far as access goes. And so, still thinking in mind of this change of culture, if you're thinking about this as the individual and it's mine, not in a selfish way, but it's mine as in no one else ever will care about this, to access it again, to sample it, that doesn't create the same culture of sharing and accessibility. The White House has come out with a statement saying that federally funded scientific research needs to become available. I'm sure many of you are familiar with that. It's caused lots of ramifications within the federal government, including changes to NSF, which has included data management plans now when you apply for funding. And they have some different guidelines as to what they mean by data. And then also, even though they don't address physical samples as data, they do say, well, what about these physical samples that relate to the data, and how do we store them? And again, they're pushing it out to the peer review of the community to say, well, how do we, what the requirements should come out of the needs of the scientists, and out of that, let them, their culture themselves. We also have different membership committees making statements. We have AGU, American Geophysical Union, saying that its policy includes data and physical objects, and that they should be made available. American Geoscience Institute also saying the same thing, making statements about the availability of data and it being important. We've got the effects of that White House memorandum pushing down into the federal government, and so as some examples of current efforts, the United States Geological Survey, actually they started this program before that memorandum. It was established as a result of the report in 2002 from the Natural Resource Council, the Science Collections in Peril. They started the National Geologic and Geophysical Data Preservation Program, where they were awarding small grants to state geological surveys to help with cataloging, inventorying, and preserving their physical sample collections. Out of some of that work, as well as some work they've been doing with the Smithsonian, they came out this summer with the Circular 1410, which is suggestions and guidelines for management of physical collections across domains, and that includes, they have biological and paleontological and earth science and a wide variety of samples, and how the federal government is addressing those collection needs. And they're also working on building a scientific collections registry, which in my mind, it reminds me of a union catalog. Those of you from library science might recognize that term, of just a link to other things. So, oh, you want to know what collections exist in the world, instead of having to hunt all over here, that might be a limited amount of metadata of here's a collection, here's how to get to it, and then put the burden on the collection itself to give you more information to provide access, but just to increase awareness of what collections exist and where. Okay, so this is just an example of the National Geologic and Geophysical Data Preservation Program, their site, and how they talk about their focusing on data. It was put into law in 2005. 2005 to fund this project, and they've been working on creating this national catalog, which again also operates as a union catalog, where the state surveys are inputting a minimum amount of metadata about their collections, and then you're able to search through this national catalog to find out where physical samples might be located, and it's again pushed down then onto the individual site to then provide more information about those collections. The American Association of State Geologists has been working on this, partnered with the National Geological Geophysical Data Preservation Program. It's a mouthful and a terrible acronym, I do apologize. But also with the American Geoscience Institute, they conducted a study last year to look at their websites and how they provide information to the public and how they can work on that. Okay. And then we get to EarthCube, which is an NSF directorate that is focusing on developing cyber infrastructure for the earth sciences, and it has two different levels. One level is the office, which just finished its test phase and started the actual office. It's located at NCAR at the University of Colorado Boulder, and with that, within the office, they direct the overarching idea of EarthCube as a membership organization that people are part of, a community, and advocating for accessibility, openness, connection of earth science data, as well as abilities to do modeling and processing in a shared way. And then underneath that is individual granting programs underneath that. There's research coordination networks and building blocks, where they're either funding groups to build the tools for this infrastructure, to build databases, architectures, other programs and databases, and I'm losing all thought of all scientific words for these things, but you get the picture, but ways of connecting this information together from a technology side. And then you have the research coordination networks that are looking at more of the community side and talking to individuals and bringing them together to work on topics and finding out what their needs are. So some examples is, this first example is iSamples, which is a group that I'm part of. It's a research coordination network, and they're funded to look at this Internet of Things, this concept of how do we document physical samples and create registry numbers, unique identifiers for them, and to advocate for citing data and connecting that across different fields. And then how do you train scientists to do those tasks too? So not just what tools can you use, but then when you're out in the field, what are the standards and best practices for documenting your physical objects, so that when you get back to the field, there's less work then to upload it. And for that, this example, what we were doing, we've got a paper coming out later this month. We were looking at workflows from students, asking them, when you go out into the field to collect research for your graduate degree, what are the steps that you take with documenting? Is there someone within your organization that helps you, tells you that there's standards of what you have to capture, what you don't? What do you do with the samples when you leave? And looking at pinch points and problem points where we can say this can be automated or this could be connected in some way. And then there's another program. This one was so much fun. I love talking about this. The EC3, the Earth-Centered Communication for Cyber Infrastructure. They brought out structural geologists, sedimentary geologists, information scientists, mobile app developers, computer scientists, linguists. They brought them out into the field. And it was a week-long field trip where they had the geologists doing their field work and allowing the others to observe and interact. And then it transitioned more to the other side of things. But the idea was, how are the scientists actually doing the work in the field? Let's not just build tools and then say, here, use this, but let's actually see what the scientists are doing, what their needs are, and how that might adapt the tools better for what they're doing. And so like some of the issues that came up that were surprise to the computer scientists were, oh, why do you still use a Brunton to measure strike and dip? Why do you not use some tool or app on your phone? And they're like, well, the magnetism of the rock or where I'm at might have a signal, might mess up that data, and it's not as accurate as when I measure it myself. So, okay, that's nice, you built a tool on the phone to automatically collect that. Now there's a level of uncertainty that I can't note in the document that this was used with this tool and not necessarily measured by hand and things like that. But ultimately one of their goals is to work on developing a database for structural and sedimentary geologists, because a lot of that field data is unstructured when it's collected in the field. It's handwritten notes, it's drawings in a notebook, it's, and then the samples and then eventually the reports, but that raw data that they're gathering doesn't have a a systematic structure across the domain, and they were discussing, well, how do we build a database? Well, how do we develop controlled vocabularies? And so seeing how the data was collected will also help influence those processes as well. And so there's a number of other efforts going on in the data-verse, if you will. But the Research Data Alliance has a couple of interest groups and birds of a feathers looking at physical objects and their associated metadata that might be either through, there's the metadata in context, providing the context for data of where it came from, why it was collected, who was doing it, when, sort of that contextual information. There's some PID groups, persistent identifier groups, looking at, again, linking between things and saying, well, and iSamples was working on this a bit too, does the project get a persistent identifier? Does the individual researcher, does the cruise vessel, if it was from a boat, things like that, get IDs? We've got the Earth Science Information Partners. They're doing a lot of work right now with data curation, and they've got a project going on looking at data maturity matrix, identifying, now that you have data and you're accessing it, how well can I rate the quality of this data? What can I say about the person who created it, if it's good enough for my research or not? How do I identify that early on? CoData is looking at data at risk. There are a number of initiatives to rescue data, which, if you think back to that slide of the rocks all over the floor, we don't want that. So we want to intervene before it gets to that point. And one really great presentation, which I meant to bring up to you all earlier, was there was someone there, they were developing a program where they were scanning weather documents from Africa, which to help with climate issues, but they're handwritten and hand annotated. Or sometimes they are machine, but the way the machine marks on the paper is not in a way that can be computer read. So they've been developing tools to get citizen scientists to be able to help translate and turn those into something more machine readable that can be then processed. And we can, because we have records going back for hundreds of years, they're just handwritten. And in some of these countries, they're at risk of loss due to lack of temperature, humidity control, or even just management. And then CSAR is a group out of Colombia that's working at creating, they call them IGSNs, unique identifiers for geological samples, where you can register your sample, and it can be on a level of scale of this is an individual sample to here is a core that has samples associated as a parent-child related to it. Water samples, biological samples, they're pushing the boundaries on that so that you can get an identifier for your sample that you can then cite in an article. So if someone would like to get more information, there can be a DOI or something that resolves back to. I think the IGSN they're working on having the IGSN resolve back to the metadata landing page to tell you more about the sample itself. But in general, this idea for the future is who should be doing the work, where should be getting done, how do we start making change and making things happen? Especially with this data deluge that's coming on to us. I mean, scientists have always managed data, they've always had data, but the level and size and scope of either how we collect, process, or manage the data is changing, and it's getting a bit overwhelming. And so who is going to do that work, and where should it be done, and when? And in a recent DLib article, there was this really nice diagram of this data product process, where there's the development, the stewardship, and then the actual production and distribution of the data. But there's this large section in the center that they have highlighted where there's this need of stewardship, where it's the stakeholders and the end users both have interest, but there's a lot of management issues involved. And I think that's where library science can really intervene and help provide structure and support in those areas. So we can think of this idea going back to thinking about a chair and what is the resource, how is it being organized, why is it being organized, how much, when, who. There are all these different things that we have to think about, and who is our audience. So you have to think about these things when you manage them, and it's less insular and less about the needs of your institution, and maybe now a little bit more outward since it's an open focus with data. And there are a lot of consequences. So in this case, I love using this when I'm teaching, because there's the idea that we can organize information on the way in or the way out. So here, this person's organization system is on the way out. He just throws it all on the floor, but when it goes to needing to recover something, that's when the organization happens. And clearly we can imagine there's a lot of work on that end that would be solved if there was some effort at the beginning. And there might even be some data loss, some loss of material and knowledge. And so I think the future is this controversy term of data scientist. And I actually got into a little discussion with Peter Fox from RPI about what is a data scientist, because you see all these descriptions where, and I love that term, unicorn, in the center, but it's a big sexy term now. It's the new area where business is hiring. But they tend to focus on like this statistics and computer skills, math skills, but that's not it. We just talked for about 40 minutes about how there's all these needs related to data information, and that's not being captured in any of these models. So I don't like any of them. I don't think any of them really work. And I really think it's a more holistic picture, because scientists, the president of CODATA actually said this last week at their meeting, the General Assembly meeting, scientists have always dealt with data. That's always been part of their job. It's just now that work is richer, more complicated. And so I think it is a more holistic concept, and we do have to think of the whole picture and how do we manage not just the information, but the access to it and the use of it. And that does remind me of a theory in archival intelligence by Yekel and Torres that really says you don't just need to know the domain, you also need to know how to operate within the institution to pull out the materials that you need. So there's this knowledge of the archive and how the archive operates. Well, whatever your archive or repository might be, of whatever it might is, of whatever scientific information, you're going to need to understand how they're organizing it, how they're using it, and how to interact with that organization in order to pull out what you need from it. Okay. And so I wasn't sure if we had enough time and if I'd tired you all out yet. So I didn't go into a lot of details, but all of this builds into what my dissertation research is on, is I'm looking at information-seeking behavior. So what is the search process that the individual scientist goes through when they say, I want to do some research. I want to see what else exists, though, before I spend time and money to go out into the field and collect new samples. How do I find out what already exists, what data is there that I can reuse, and document that process in order to build a model that we might use either for training or developing better databases, information retrieval systems, or even changing the processes that we're currently doing so that they can more mirror the individual scientist's needs. And ultimately, I do think that that's going to underscore this need for training both of the scientists and how to better manage their data in order for it to be outward accessible, but also for information professionals to figure out how to manage scientific data and be able to interact with that different animal, if you will. But our ultimate goal in life is to push button, get research, and make progress. Like, we want to simplify this so that the scientist is not burdened with having to do a lot of this management work and is able to do the science that they want to be doing. And so that was, I'm trying to look at the time. Yeah, I'm just going to wrap up here, I guess. But thank you very much for listening, and I hope we have some good questions and discussions. I'm excited to hear what fields you all are here from. And thank you all for listening.